Well, good morning. This is 10 o'clock on Wednesday, the whatever 18th, whatever it is of uh, March 18th. And this is Calculus 1. I don't have any students logged in yet that I can tell. If you are, please log in for me. I don't know what you can or can't see. My guess is you can see the top of my head because that's what I see in my screen. But as soon as you log in, say something so that I can get you marked as present today. This is my first time doing a Zoom with you. I did 4 yesterday. They seem to work okay. So I hope that some of you will be logging in soon. But in the interim, let me go on and get started on today's class. We're in Chapter 4, Applications of Differentiation, Section 4.1, Extrema on an Interval. And last time we had talked about relative extrema and just were beginning to introduce the concept of critical numbers. And that's where we begin today on page 208, very top of the page. In fact, I thought it was a slide before that. Yes, I'm sorry. There's a slide before this. We did example 1 last time, and it said, if you recall from last time, and I know about 5 or 6 of you, four of you were there most of the time. One showed up very late, but anyway, in example 1, that each relative extremum, that's a relative maximum. Oh, Houston's here. I saw your name pop up. I don't see your face, but that's okay. I can live without. I didn't say that. Houston is here. Okay, good deal. Hopefully. Yes, and Andy's here. Excellent. Way to go.
Hello.
Yes. Is that Andy?
Yes, sir.
All right. Good to see you or hear you. And I see JJ. Okay, and let's see, I guess that's all 3 that are here. All right.
I think the other ones were in that other collaboration that's like in Blackboard.
Okay, you've been doing Collaborate in Blackboard?
Yeah, I think that's where they're at right now. You want me to tell them
Oh, no, yeah, I told them we would be in Zoom, I thought. Yeah, tell them to check their Blackboard, not Collaborate, but check Blackboard. There's a message, the same place you got your code. That'll get the code. The ID is 408-329-967, and there's dashes between each 3 digits.
Well, mine just let me join it instantly. It didn't ask me for the code.
Yours did what?
Mine let me join instantly. I didn't ask for the code.
Oh, you didn't? Oh, okay. Well, glad you joined. I don't know how it is on your end. We're supposed to send the code, so I set the code, but I guess, good deal. I'm glad you're here. Oh, anyway, I'll go on and continue. In the example 1 we did last time, that at each relative extremum, and that's the singular, okay, the derivative either is 0 or does not exist, okay? At each relative extremum, the derivative, first derivative, is either 0 or it doesn't exist. The x values at those special points are called your critical numbers, okay? Now, this figure that you see on the screen here, and it's on page 208 in the text, shows 2 examples of this. That first one, where you have a cusp, that's what you call that, the first derivative doesn't exist because the first derivative, let me get my pen set up. Okay, the first derivative is going to infinitely large coming from this side, but it's infinitely negative going on this way. So certainly the derivative does not exist at the point C. Alpha prime of C does not exist. on the second one here, the B, I guess you would call it, this has a horizontal tangent line, meaning the first derivative is 0. Now, we're going to get to this later, but I just wanted to point it out to you now, okay? Just because the first derivative doesn't exist or is 0, that doesn't guarantee that you're going to have a extremum, but you still consider that, at least for right now, your critical numbers. Then you investigate to see. This one, obviously, is going to be a relative. In fact, it looks like an absolute maximum. This also is a relative and or absolute maximum. Okay? From what we can see, that would be, both of those would be relative maximums. Okay? So, moving on to slide 2. Have any of the others found their way to us now, or do you know? Okay. I'll keep going.
Well, one actually left, and I think they're joining. And Emmanuel,
Right?
he's asking me what to do, and I just told him.
Okay. Okay. Did any of you see the announcement or email through Blackboard?
I did see the announcement.
What's that?
I did see the announcement. That's where I got the, and it was in the archives, and that was where I got the code and the password.
Okay, right. Now, I'll explain a little something. Yesterday, I was on the free version, and the free version, I couldn't pass out the code until right before it started because we were limited to 40 minutes. Though 3 of the 4 classes went over 40 minutes, and they didn't stop us. The other one they did, but then we just did a new code. However, last night my wife split the, we bit the bullet and paid the $15 to get the paid version. So I have it for a month now, and so I will be able to send the codes earlier. At least that's what she told me. Okay, so I will try to get these codes to you sooner now, but I didn't find that out until I was just down talking with her just before I came up to start class today. So in the future, now of course you know the good news, bad news, right?
What is it?
Well, the good news is spring break week is next week. And the bad news is we won't be meeting then. So there will not be any meetings next week, Tuesday, Monday or Wednesday of next week. Sorry about that, folks, but get over it. But then when we meet again, the following Monday, I think that's the 30th, then I will try to have your codes out to you sooner because I'll still be on the paid version, and I can, at least Karen told me that I should be able to get the codes to you much sooner next week. I didn't know it this time, but we just got it last night, but I didn't know that I could give you the codes earlier. I thought you were also limited, since you haven't paid, to 40 minutes. She said, no, I'm the host, I'm the only one that's limited. So one of the students. Jermanuel's here?
Yeah, he's joining.
Oh, welcome, Jermanuel. I don't see you yet, but glad that you're here. Okay. And I was sort of expecting Jonah to be here because he's the one who's been on it before. He told me a lot that I learned about Zoom. So hopefully he'll be coming in sometime soon.
What about our tests? Are we going to be holding on to them?
What's that again?
What about our tests? Are we going to be holding on to them?
No. What I would suggest, if you're through with the test, scan it and email it to me. Okay? Is that okay with you? Now, Dr. Davis, I was talking with the dean this morning. That's why I wasn't more prepared and got ready sooner, is because I had a long conference call with her and then an individual call with her after the conference, other people in the conference left. But she said that you can also post things through Blackboard. Now, I haven't investigated. She told me where to go. She said quick link. If you go to the homepage of Blackboard, there's a series of blue tabs at the top of the page, and then there's one big gold tab, and that says quick links. And she said when you click on that, there is something that goes there's a student resources and a faculty resources. If you go to the student resources, it tells you how you can do all sorts of things. Was someone saying something?
No, it's not. I'm at work. I have a question.
Oh, no. I mean, Cal's here. Good. Okay.
I didn't get the test because I wasn't in class on Wednesday.
Oh, isn't that too bad? No. No. I will email you the test probably today. It'll come as a PDF. My wife's going to try scanning it with her phone rather than setting up a scanner here at the house. She's going to try that, and we'll see if it works. So you may be our first guinea pig.
I need one too.
And here's Jermanuel is here. I see the headset anyway. Okay. But I saw your name. Yeah, I see you. Got it. Okay. And I think he's really listening to music, but he's pretending that he's listening to me. Okay, that's good. Okay. Okay. So I will try to send anyone who was not here the day. Okay. How many of the rest of you did not get the Chapter 3 test? Okay, Jermanuel didn't. Houston raised his hand. Good. I see a little block that says that. Okay. And Kyle. And JJ, you got yours, right? Okay, good. Okay. I guess we got that covered then. So I'll try to send, let me make a little note here. Houston, Kyle, and Jermanuel, send them the test. Okay. It'll be in PDF form, and then when you finish it, scan it and send it back to me. Y'all okay with that? Okay. All right. Good deal. Okay. Back to any other questions or about any of this mess stuff. Everybody's all right. Okay. Then
Put a shirt on, Jermaine.
what was that again? Never. Maybe I shouldn't have heard.
Put a shirt on. We're in a session.
All right. I must say I taught 4 classes yesterday. The first 2 classes, nobody showed up. Of course, they had very little time to find out about that. The second class, the third class, one person showed up, and I was having trouble getting him to participate, and finally said, "Can you wait a minute?" I said, "Well, sure. What's wrong?" He said, "I'm driving." I went, "What?" So that's why he couldn't participate. And then the fourth class, several people logged on, but I couldn't get one of them to say a word. So thank you for being freer at this than the others were. So y'all are, it's, of course, always been my best class. So why am I surprised? All right, moving on to, I have to put on my high water boots here. No, it's not water. Okay. Relative extrema and critical numbers. Okay, can y'all see the screen? Some of them yesterday couldn't see the screen. Can you see the screen? Okay, you see the PowerPoint, right? Excellent. Okay. We were just talking about these are your critical points. We identify them by taking the first derivative. If the first derivative does not exist at a point, that's a potential critical point. And if the first derivative is 0, that's another potential critical point. Okay, they call them critical numbers. I usually call them critical points, but I'll try to say critical numbers because that's what they say. Any questions? Okay. So here's the definition of a critical number. If f is defined as c, let f be defined as c. Now that's the function, not the first derivative, the function. It has to be defined at c. If it's not defined at c, you can't, it won't have a critical number. It must be defined at some value c. And if f prime of c is equal to 0, or if f is not differentiable at c, in other words, the first derivative does not exist at this point c, then c is a critical number of f. Okay. Now this is a critical number. Now we started this whole mess by talking about relative maximum and minimum, extrema. Okay. This is just defining critical numbers. This doesn't guarantee it's an extreme value, okay? And that's what we're going to hit to next, or we're going to hit part of it next, okay? Notice that in this definition, the critical number C has to be in the domain of the function f, but C does not have to be in the domain of f prime. It has to be in the domain of f, but not in f prime. If it's not in f prime, that means it doesn't exist there, so it can be a critical number, or if the first derivative is 0, then it's a critical number. Now, your relative extrema, relative maximum or relative minima, occur only at the critical numbers. You will not find a relative extrema at any other value. Okay. Remember your absolute extrema, they can be at your endpoints of your interval. Those are not critical numbers. Those are the endpoints of your interval. But the relative extrema, those are ones within the interval. Those will only occur at critical numbers. If f has a relative minimum or a relative maximum at x equals c, then c is a critical number of f. Now, what I'm keep hinting at, and I'm going to say outright now, the reverse is not true. Okay? Just because it's a critical number doesn't guarantee it's a relative minimum or maximum. Sure is one to investigate, but it doesn't guarantee. Okay? So let's move on. That theorem in your text, you'll find a little proof of that, so you can certainly go through the proof. On the side of that, they have a little blurb on Pierre de Fermat. I don't know if I'm pronouncing that right, but he was trained as a lawyer, and mathematics was more of a hobby for him than a profession, and yet he was one of the greatest mathematical minds to exist. He made many contributions to analytical geometry, number theory, calculus, probability. In letters to friends, he wrote many of his fundamental ideas for calculus long before Newton or Leibniz. Okay? And Theorem 4.2 is one of the theorems that is sometimes attributed to Fermat. Now, how did they have critical numbers before they had derivatives? I don't know. Okay, I can't answer that question. They probably called them other things then, just relative maximum or minimum of a function. Those kind of things they did talk about, but they didn't have first derivatives not existing or equal to 0 because they didn't have derivatives. So, but anyway, Fermat, just a little on the side here. By the way, this information here, this is not enough for your paper, but it does give you ideas where to go to maybe get ideas for a paper. Your book cannot be your source for your paper. You have to, it can be the source for the idea, but not for the paper itself. Now, on that subject, let me go back and review in this, one of my best classes ever, of course. How many papers have I got turned in? 0, okay? Not a single paper in yet. Please get those in. We're running, we're in the second mini-term already. We only got about a month left, a little over a month. But with spring break in there, it's just not much over a month. And folks, please get those in. Things are going to get crazy. And by the way, everything I'm reading and hearing, they say we have online stuff this week. Of course, today's our last day for it. Tomorrow is another day for it. And then we have spring break week next week. I told you the bad news there. And then we have one more week of online stuff. And then they think we'll be back on campus. I don't believe it, okay? This thing is not even reached its peak yet. So I think it'll still be climbing first week in April. So I'm fully convinced we're going to be doing this, I think, for the rest of the term. So get used to it. We're here. So please get those. So if you finish a paper, email it to me. I can take it either in Word format or in PDF. Okay? If you happen to have WordPerfect, I can take it in WordPerfect format, but most people don't have WordPerfect. I do, but most people don't. But either Word format or PDF. But get them to me. Okay. We're moving on to page 209, finding the extrema on a closed interval. Okay? These now can be absolute extrema as well as relative extrema. Okay. Theorem 4.2, the one we just were talking about, states that the relative extrema of a function can occur only at the critical numbers of the function. Relative extrema, remember that. Knowing this, you can use the following guidelines to find extrema on a closed interval. Not an open, but closed. Okay? Relative extrema are they occur within the interval. They do not include the endpoints. So when you do deal with a closed interval, you have to consider the endpoints. So here's the guidelines for finding extrema on a closed interval. To find the extrema of a continuous function f, needs to be continuous, on a closed interval a to b that includes a and includes b and everything in between, use the following steps. First, find the critical numbers. How do you find the critical numbers? Someone answer. Help me out. What's the Jesus answer in this course? Take a derivative, of course. Okay? So you take your derivative, and what do you set it to? One of two possibilities for your derivatives. Second? Okay, either it's going to be 0 or it's going to be at a place where it does not exist. Those will be your critical numbers. Take your first derivative, set it equal to 0. Any values in that interval that make that first derivative equal 0, those are critical numbers. Any numbers in that interval where the first derivative does not exist, those are critical numbers. Okay? Now, Jermanuel, I'm sorry, did you have a question? I saw you pop up here.
Oh, no, sir.
No, okay, got it. Okay. So those are two critical numbers, okay? Or not two places to look for critical numbers. So find the critical numbers of f in a and b. Take a derivative, set it equal to 0, find where it doesn't exist. Number 2, evaluate f at each of the critical numbers, okay? Now notice that in AB, these ABs here are in parentheses, meaning the open intervals a to b. Because you don't find derivatives on an open interval, on a closed, you don't find derivatives at an endpoint. You only find derivatives inside the interval. So that's on the open interval a to b. Number 2 is at the open. Evaluate the function at each critical point. Okay? Critical number. Okay. Number 3, then evaluate f at each endpoint, a and b. Why did they put a closed b? Just say find f at a, f at b. That's what it means next. And then, number 4, the least of those values, the value you found at each critical number, the f at each critical number, and the f at each endpoint, look at the least one of those, that's your minimum. Okay? The greatest one of those, that's your maximum. Okay? That's how you find them on a closed interval. So here's example 2. This is on page 209. Let's do it. Find the extrema of this function on this closed interval from -1 to 2. What's your first step? Take a derivative, f prime of x. Okay. Y'all are participating really well. What is that? Say again? A little louder. 12x to the third minus 12 x squared. Perfect. Okay? And what do we do with that? Okay, you took a derivative. What do you do with it? Set it, what do you say?
Set it to 0.
You set it to 0, exactly. Set it equal to 0. Now, how do you do that with this one? What's the F word? All right. And how does this factor? What do you always pull out first? Greatest common factor. And what is the greatest common factor? 12x squared. Perfect. What's left? X minus 1. Perfect. Set that equal to 0. All right. What's that first factor give you? 12x squared equals 0. What value of x will make that true? Well, certainly 12 is not equal to 0, right? So x squared has to be equal to 0, right? Divide away the 12, okay? So x squared equals 0. What's the only value for x, values for x, that will make that true? There's only one. X equals 0. Now, that's a double root, by the way, but we would worry about that in precalculus algebra. It may come into play here, but there's a 0. Okay, that's one factor. What's your other factor? X minus 1. Set that equal to 0. And what does that give you? Did someone say x equal 1? Say yes. Yeah, x equal 1. Okay. Now, the next question you ask yourself, are all of these values in the interval? Yeah. 0's in between minus 1 and 2. 1's in between minus 1 and 2. Yeah, they are. Both of these are in the interval. Now, actually, that 0 is a double root, but we're not going to worry about that. It's just x equals 0. So, are there any places where this derivative, what's the other thing we consider about the derivative? Where it's equal to 0, we did that one. Or where it doesn't exist. Is there any place that derivative doesn't exist? No, that's a polynomial function. 12x cubed minus 12x squared. Polynomial function, they exist everywhere. Domains, all real numbers. Only place they might not exist is if you had a variable in the denominator. Then you'd have to make sure that doesn't make the denominator 0. This doesn't have any denominators. If you have a variable in a square root, you have to make sure what's in that square root does not go negative. This doesn't have a square root. The other one would be if there was a log, natural log or any other log in here. You know the log of the variable inside a log, the quantity inside the log cannot be 0 and it can't be negative. Neither one of those. So we don't have any of those cases. We have a polynomial function that's defined everywhere. So these are our only two potential critical numbers. So what was the next thing it said to do? Evaluate the function f of x at 0. And I think I can even do that one. What would that be? Now this is f of x, not f prime of x. Anybody? 0. Okay. And how about f at 1? What would that be? -1. Perfect. Okay. Now, we have a potential maximum of 0 and a potential minimum of -1. But we're not through yet. What's the other things we've got to do? Say again? Anybody? The endpoints, you have to evaluate them as well. So what's f of -1?
Is it 0? No.
Okay, let's try it. Let's do it a step at a time. 3 times a -1 raised to the 4th power minus 4 times -1 raised to the 3rd power. What is -1 to the 4th power? Positive 1. So this will be a 3. And what's -1 to the 3rd power?
Now that is
Okay,
negative.
-4 times -1 is?
Positive 4.
Plus 4. So this is? 7. Ding, ding, ding. We have another candidate for relative or maximum. Now the 0's out of the picture because that can't be a minimum or a maximum. Okay? So -1 seems like, or f of -1 seems like it could be a maximum. Okay? But we got one more to try, and what's that? 2. Okay, so let's do f of 2. Oh, this is really going to take some effort, isn't it? 3 times 2 to the 4th power minus 4 times 2 to the 3rd power. And what is 2 to the 4th power? 16, did someone say? Okay. Minus 4 times, what's 2 cubed? 8. Okay. And 3 times 16 is?
48.
Oh, good. Okay. Minus 32. And that's equal to? Second? 16. Ding, ding, ding. We have another winner. Okay? 16 wins as the maximum, and -1 stays as the minimum. Okay? You see how that works? Does it make sense?
Yes.
All right. Take your derivatives. Set it equal to 0. Find all the x values that make it 0. Those are critical numbers. Okay? Then see if there's any places where the first derivative doesn't exist. That's a critical number. Okay? Since you have your critical numbers, fill in each one, evaluate the function, not the derivative. You know what derivative is. Find the function at each of those critical numbers, evaluate it. Okay? Then, if it's a closed interval, you have to evaluate your endpoints as well, see what those are, and whichever is the greatest of those, that's your maximum. The least of those is your minimum. That's how we did it. Let's see how they did it. Does this make sense? Does anyone need this up a little longer?
No, you're good.
Okay, I know I'm good. Do anyone need it up? No, I'm just kidding. Okay. It wasn't that funny. Okay, now. All right. So let's see how they begin by, guess what? Differentiating the function. Okay? So the function is 3x fourth minus 4x cubed. Take a derivative of that, 12x cubed minus 12x squared. Y'all did it perfectly. Then you define the critical numbers on the open interval from -1 to 2. Find all the values for which that first derivative is 0 and all the x values for which it does not exist. Okay? Let's take care of the does not exist right now. It exists everywhere. It's a polynomial function. The first derivative exists everywhere. So let's focus on the zeros. Factor first, 12x squared times x minus 1. The first factor gives you x equals 0. The second factor gives you x equals 1. Okay? Those are all the critical numbers. So evaluate the function, not the derivative, the function, at each of those critical numbers. Because f prime, okay, they went back. Because f prime is defined for all values x for polynomial numbers, you can conclude those are the only critical numbers of f. We already concluded that. Okay. So, evaluate each of those. They like to do them in little boxes, so do them in little boxes if you want to. Oh, did I blow it? No, I got it right. Okay. They started with the -1 because that was a left endpoint, and evaluated it and found that was 7. They did the first critical number 0, found out that was 0. The second critical number 1 gave us a -1, just like y'all found, and the right endpoint gave us a 16, just like y'all found. And look at those, which is the least, -1. There's your minimum, which is the greatest, 16. That's your maximum. You found the absolute minimum, absolute maximum on that closed interval. Does that make sense? Let's see if they show us a picture. There it is. Okay. The left endpoint at -1, 7. You see that 0, there's that value. Okay. And then you have a minimum at 1, -1, and then you have your maximum up there at 216. Now, let's get back to that double 0 that we had here. Remember, I kept saying that's a multiple 0. Look at what happens there. This comes down, it's decreasing, decreasing, decreasing. It flattens out near 0, giving you a 0 first derivative, but then it continues decreasing again. This is neither a local minimum nor a local maximum, because it neither is the least value around it, nor is it the greatest value around it. It's a neither. We'll later call it an inflection point, but that's beside the point now. But this is a absolute minimum. It's also a relative minimum. Okay? This is neither a relative maximum or relative minimum. You only talk about relative maximum, relative minimum of your critical numbers. The absolute may include endpoints. Okay. Does that make sense?
Yes, it does.
All right. Let's move on to, I believe this will be the next page, 210. I'm trying to find the verbiage here. Oh, here it is at the bottom of 209. Sorry, I jumped too soon. I don't jump well. Okay, in figure 4.5, the one we were just showing, note that the critical number x equals, oh, look at that, they saw this too. The x equals 0 does not yield either a relative minimum or a relative maximum. And that tells you that the converse of theorem 4.2 is not true, which I kept saying. Just because it's a critical number does not guarantee a relative maximum or minimum. However, if it's a relative maximum or minimum, it's got to be a critical number. So it works one way, but not both ways. Okay? In other words, the critical numbers of a function need not produce relative extrema. They usually do. You expect them to, but they don't have to. But every relative extrema has to be a critical number, occur at a critical number. So you could kind of do it this way. Critical number, relative extrema, okay? If it's a critical number, it doesn't guarantee it's a relative extreme, but if it's a relative extrema, it guarantees it's a critical number. So the arrow points in one direction, not both directions. That's a silly way to do it, but that's actually in symbology, that's how they represent this. Okay. And that's the last slide in the section. So let's do, it's not the last example in the section, there's two more, examples 3 and 4. Let's do example 3. Find the extrema of f of x is equal to 2x minus 3x to the 2/3 on the interval -1 to 3. Okay? Now, whenever I see a fractional exponent, that usually is a signal you might have some problems here, folks. So the first thing I'm going to do is make sure that the function's defined everywhere on that interval. Now, since that is a positive 2/3, that means the cube root of x squared. That's what x to the 2/3 mean. Well, when you square a number, positive, negative, or 0, you're going to get a positive number, or 0, okay? And then you take the cube root of a positive number, or 0, that's always defined. So yes, there aren't any places on this interval where that's not defined, okay? In fact, there's not any places anywhere where it's not defined. Cube roots you can take cube roots of positive numbers and negative numbers, okay? Square roots you can't, fourth roots you can't, any even root you can't, but odd roots you can. So cube root, perfectly fine. So number 1, this function is defined everywhere on the interval. They didn't say that, but it's not a bad idea. What do you do next? Take a derivative. F prime of x is equal to
2.
Help me, this is the hard part. I need help here.
2.
2
Minus
anybody?
2x
minus 2x to the
Negative 1/3.
-1/3. Excellent. Okay. 2 minus 2x to the -1/3. Okay. Now, what are we going to do with that derivative?
Set it to 0.
Say again?
Set it to 0.
Set it equal to 0. Sounds like a great idea. Okay. Now, anytime I'm taking a derivative or doing anything else in calculus, I usually like to have it in exponential notation like they gave us and like we did. However, when I'm trying to solve an equation like we have now, I kind of like to get it back in radical notation. So let's do that if we can. I'm going to do two things at once. I'm going to move the minus to the other side. So this is going to produce 2 is equal to 2 times 2 over the cube root of x. Would you agree that's the way that could be written? I did two things at once. Number one, I moved the minus sign to the other side, but then I changed the x to the -1/3 to 1 over x to the 1/3, which is 1 over the cube root of x. Okay with that? Yay or nay? You all right? Is that okay? Any questions? Does that work? I hear total silence here, okay? Is that okay? Is what I did legal in most states? Okay. Let me take it a step at a time then. Let's first add 2x to the -1/3 to both sides. Okay? Okay. So now we have 2 is equal to, because that goes to 0, 2x to the -1/3. Well, I'm going to rewrite that x to the -1/3 as 2 over x to the 1/3. Is that legal? Isn't that what that minus exponent means? Move it downstairs, lose the negative sign. And what is x to the 1/3? That is the cube root of x. So 2 is equal to 2 times the cube root, 2 over the cube root of x. Is everybody okay with that? Any questions about it? Okay, I'm going to assume silence means assent, that you're okay with it. Is that all right? Now, one thing sort of pops in my mind first. I can divide both sides by 2, and this becomes a 1, and that becomes a 1. So this is going to be 1 is equal to 1 over the cube root of x. Okay? Now, there's two questions we have to ask about this first derivative. What are they? We set it equal to 0, okay?
Places where it does not exist.
Say that again.
Are there any places where it does not exist?
Yes. Is there any place where that derivative does not exist? Okay, well, I guess we set it to 0, so let's just deal with that one first. Let's multiply both sides of this equation by the cube root of x. That'd be the cube root of x is equal to 1, right? Multiply this side by cube root of x. I can't write. It's not writing, okay? Multiply this by the cube root of x. These go out, and you have cube root of x is equal to 1, okay? Now, what value of x makes that true? What value of x makes that true? Cube root of x equal 1. How could we solve that? How do you undo a cube root? I see Kyle's name popped up, but I don't hear anything. Are you? You do what? It's equal, x equal 1? That's it. Okay. Now, the answer to my previous question was, How do you undo a cube root? Cube both sides. Cube this and cube this, and you get the cube root of x cubed, or, yeah, however, that gives you x. 1 cubed is 1. So, yeah, that's perfectly correct. So that's where your function is equal to 0. X equal 1. That's a critical value. That's going to be a C. Okay? One of your C's. Now, the next question, let's go back to that derivative again. Okay? F prime of x is equal to 2 minus 2 over the cube root of x. Okay? I'm writing it that way now. Is there any place where that doesn't exist? Two things we consider about the first derivatives: where they're equal to 0 or where they don't exist. We've already found the one and only one place where it equals 0 at x equal 1. Is there a place where that doesn't exist? Anybody? Still see Kyle's name? Oh, okay.
Any x's that are negative?
Say it again.
Any x's that are negative?
No, you can take the cube root of negative numbers. You can't take square roots. You can't take fourth roots, but you can take cube roots. How about anything else? What other thing might bother you a little bit? What is the other thing that you can never do? There's a few, but there's several things you probably shouldn't do, but there's some things you can never do. Divide by 0. You can't divide by 0, can you? Can you make that denominator 0? What value? X equals 0. Okay, that's another critical value. So we've wound up with two critical values. One where the first derivative is 0, one where it doesn't exist. Okay? Anything? Oh, what do we do next? Evaluate the function f at both of those values. Okay, now the book sort of likes to do the lowest number first, so okay, time out again. First thing, are both of these values inside your interval? Yes. Okay, got it. Okay, now, I don't necessarily like the way the book does it, but I'll do it the way the book does it. They start with the least value. So here's a value, -1, 0, 1, and 3. Let's evaluate it at all three places. F of -1. F of -1. That's 2 times -1 minus 3 times, I'm going to write it this way, the cube root of -1 squared. That legal? We're doing the function, not its derivative, the function. Everybody happy with it? So this is 2 times -1 is -2 minus 3 times, what is -1 squared? Is 1. And what's the cube root of 1? 1. All right. So what does this give us? -2 minus 3 equal -5. Perfect. Okay. We have a potential maximum or minimum. It's the only thing we got now. Okay. So let's go to the next one. That one would be 0. F of 0 will be 2 times 0. Remember, you use the function, not the derivative. Minus 3 times the cube root of 0 squared. Okay? Anyone want to make a guess of what that is?
Would it still be 0?
That's 0, of course. Because 0 squared is 0, cube root of 0 is 0, 3 times 0 is 0, 2 times 0 is 0, everything's 0. Okay, now, so we have a potential maximum here, a potential minimum there. Let's continue. Next would be f of 1, your second critical number. And this will be 2 times 1 minus 3 times the cube root of 1 squared. All right, anyone want to make a guess of what that is? Negative 1. It sounds like it is to me too. All right, that's not going to be a relative maximum or a minimum, is it? It's in between -5 and 0, so it's out of the picture here, okay? Not even going to get onto the practice field, okay? So let's go to the last one, which is 3. F of 3. I don't have room at the bottom, so I'm going to do it up here. F of 3 is equal to 2 times 3 minus 3 times the cube root of 3 squared. And this is the pain in the neck one. Okay? 2 times 3, of course, is 6 minus 3 times the cube root of 9. Okay? Now, I don't know what the cube root of 9 is. Okay? I know it's more than 2, though, isn't it? Because the cube root of 8 is 2. So this is a little bit more than 2. Okay? So you got 6 minus 3 times something a little bit greater than 2. That would be something a little bit greater than 6. 6 minus something a little bit greater than 6 is not going to be very, it's going to be negative, but it's not going to be very negative. So in my mind, -5 wins, and whoa, 0 is your maximum. Boy, you don't want that to be what I say at the end of the term, is it? 0 is the best score you got. Oh, never mind. Okay. All 3 of the others were negative. -5 was the winner as the absolute minimum, and 0 was the absolute maximum, but it certainly was a relative maximum as well. Okay? Now, if you're looking in your book, and I don't have any way to show this in the book, but on page 210, top of the page there, you'll see that one. At -1, -5, that sure was the minimum value, and 0, 0 did turn out to be the maximum. You did have a local minimum at this value. That's a local minimum at 1, -1, and then you have the last one. They really were creative here, and they said it's, say again?
Oh, my bad. I'm open with my mouth.
Oh, okay. They didn't even evaluate it. They just said 3, 6 minus 3 times the cube root of 9. That's sort of cheating, but that's exactly what it is. But it's a number slightly negative, but not very negative at all. Okay. Any questions on that? The graphs help you visualize it, but you know, we figured out all this without the graph. Okay. Well, that means we move to guess where? Example 4. And here's our function here. And by the way, especially if you found this one challenging in some way or another, you can go to larsoncalculus.com for an interactive version of this type of an example. Here's your function. F of x is equal to 2 times the sine of x minus the cosine of 2x. Okay. I was going to see if Jemanuel could plot this for us real quick. No, let's not do that. This is not an easy thing to graph. Okay. So what? Oh, I got to give the interval on 0 to 2 pi. All right. What's our first step? We're looking for our extrema, the extreme values on that closed interval.
I think he needs a little help from
Okay. Take a derivative. Sounds like a winner. Okay. First derivative is? No, you got to evaluate it first. I'll get it started. 2 times derivative of sine x, cosine x. Okay. Next. Did I hear a minus?
Yes, sir.
Okay, I'll put a minus down. What's the derivative of cosine 2x?
Negative sine of 2x.
Okay, the negative sine of 2x certainly is going to be there. But then you got a chain rule issue.
2x.
Times what? I heard something. 2. Derivative of 2x is 2. Buy that or not? Okay. Where do we go from here? Help me, somebody. Set it equal to 0. That sounds like a winner. Okay. Now, I can think of one thing to make that a little simpler. And what's that? Yeah, divide out a 2 from everything on both sides. And that's equal to 0. You can do that if it's an equation. You can't do it if it's just an expression, but you can do it if it's an equation. So now our equation is cosine x plus sine of 2x is equal to 0. All right. Now, that's sort of a pain in the neck looking equation, isn't it? I saw some heads nodding, so I assume you agree. Is there any way you can simplify that? Oh, no, we don't have to use trig identities, do we? Of course, that's why you had trig before you had this, right? Can anyone remember how we can... Here's the problem. This has an argument of x, that has an argument of 2x. Those are going to be hard to compare unless we can get right this in terms of trig functions of x. Does anyone remember the good old double angle formula? Oh, I saw lots of hands go up, didn't I? Oh, what is it? If nothing else, if you have your books handy, go to the front inside cover of your book. There's one page there that's sort of cardstock, and on the front side of that is derivatives and integrals, but on the back side of that is trigonometry.
The sine 2x can be 2 sine cosine.
Yes, 2 times sine times cosine. 2 sine x cosine x. That equals 0. Now, if you can read my sign, it's pretty ugly. Okay, that's a little better. Okay. What can you do with that?
Get rid of the cosines.
Oh boy, he likes to get rid of things, doesn't he? What do you mean by that? What's the F word? Factor out the cosine. You don't get rid of it. Goodness gracious. What does that leave you?
Sine x.
Well, you have a 1 here, don't you?
Yeah, my bad. 1 sine x.
Okay, 1 plus 2 sine x. See, he really wanted to get rid of that cosine, didn't he? Okay. Now, what can you do with that? You have the product of two entities equals 0. What can you do? Product of two things equals 0. What can you do? Help me.
Separate them.
Yes, either cosine x is equal to 0. That's why we didn't want to throw it away, Andy, okay? Or 1 plus 2 sine x is equal to 0. Perfect. Okay, let me clean up my 2 there a little bit. Okay. Whoa, too much. Okay. All right. On the first one, on the interval 0 to 2 pi, what values of x in that interval will make the cosine equal to 0? Oh, man, we have to know our trig functions? It's too much to ask. Okay, did someone say something? What that? Say again? Yeah, pi halves will certainly make that a 0. Any others? One more, by the way. Hey, Jonah's here.
Oh, I've been here for a while. I've just been getting situated.
Okay. Yeah, you're always first one in the classroom, and you're... No, I'm just kidding. Okay, good deal. Do you see where we are now? I think that meant he was propping himself up in bed. That's what he means by getting situated, right? Oh, never mind. You wouldn't say that. What's that?
That's exactly what that means.
All right. So we determine where cosine x is equal to 0. That happens at pi halves. Any other values between 0 and 2 pi where cosine would equal 0? 3 halves pi. 3 pi over 2, and all the others are outside that domain. Okay? So that gave us that. Let's go to the right-hand equation. What do we do with that? Here's what we're going to try to do. 1 on the other side. Yes, subtract 1 from both sides. I like that idea. That goes to 0, and you get 2 sine x is equal to negative 1. And now what do we do? Divide both sides by 2. Okay? And that gives us a sine x. That's not 6, okay? It's a sine x. It's even worse if it was a secant x, but never mind, okay? Sine x is equal to negative 1/2. Uh-oh. Are there any values between 0 and 2 pi where the sine of x is negative 1/2? Oh, I hear the gears grinding on it, okay? Here's what I like to do, okay? I like to draw graphs. Don't you like to draw graphs, okay? A sine starts here, goes up to 1 at pi halves, down to 0 at pi, down to negative 1 at 3 halves pi, and up to 0 at 2 pi. Well, there's got to be something here and here where that's going to be. If this is negative 1, there's got to be 2 places there where this is negative 1/2. Any idea where they might be? Don't know if y'all remember what we called the reference angles. Where is sine of x equal to 1/2? This is a different question. Anyone remember the value for x? It's one of our favorite ones, remember? One of those that was either 0, pi 6, pi fourths, pi halves, or pi thirds, or pi halves. One of those. Oh boy, I got to talk with some trig teachers, I think. Okay. Anyone want to make a guess? I gave you multiple choices there. Maybe you prefer unit circle type. Oh, goodness, sorry. I just blew you up. I don't know how to undo
You're
that.
asking for like the degree.
Okay, let me, I did something.
You're asking for the fraction.
Okay, hold on just a minute. I need to minimize this. I'm going to try this and see what happens. Okay. That might actually be better. Move this back up here. Can y'all see what I'm doing? I don't know if you can or not. Okay. Does this help any? Sine is y over r, and if this is a unit circle, this is a 1 here, and your y is your opposite value. Okay? So something like this. What angle would then be 1/2 over 1? Hint, it's a small angle. Okay, someone said something earlier.
30 degree angle?
I can't hear.
30 degree angle?
Did you say pi thirds?
30 degrees.
Oh, 30 degrees. Absolutely, the 30 degrees. And since I'm guessing the book's going to give this answer in, yeah, since they gave the interval in pi's, in radians, I don't think they want the answer in degrees.
Pi 6.
Pi 6. Okay. Now that gave you pi 6. So basically what we've got here, your 1/6 pi past, what value I say this was? This is pi halves, pi, 3/2 pi, and 2 pi. Your pi 6 past pi. So what would that be? Pi 6 past pi. Add pi 6 to pi. 7/6 pi. Okay? Now, you're pi 6 short of 2 pi here. Here are your two angles, this one and that one. Okay? This is pi 6 here and a pi 6 there. Well, it's what? 11 pi over 6? Perfect. Excellent. There we have it. Those are the 4 points, 4 values, 4 critical values. These are all C's here. In between, in this interval, 0 to 2 pi, where this first derivative is 0. Okay? What's the next thing we consider? Where the first derivative what's the second thing we consider? Where it doesn't exist. Okay? Now, here's your first derivative again. I'm erasing things so you can see it. Forget about setting it equals 0. We've already done that. There's your first derivative. Is there any place where that doesn't exist? The answer, no. Because sines and cosines are defined everywhere. There's no vertical asymptotes, no places they don't exist. If you did a sine function on the board, it'd go around and round and round and round and round the room and never end. Same with cosine. So this first derivative is defined everywhere. So we found our 4 critical values. Now what do we have to do? Yes, plug these in to our original function. Not into your derivative, they're going to be zeros. So I'm going to, just because I need more room, I'm going to erase everything but the critical values. Okay? Critical numbers. I'm sorry, the book calls them numbers. I call them values. Okay? Okay, I hope y'all got it all as we were doing it, because I'm erasing like crazy here. I may even erase my scratch work here. Is that okay? Oh, I erased too much. Probably could have erased everything and just written back what I left, but I didn't do that. Okay. All right. Into the original function, not the derivative, we'll plug these in. Now, do you want to do them in the order you get to them, or you want to do them in any order, whatever? I don't care. Oh, and what else do we have to do? Not just these 4 values, also endpoints. Okay, so I know the first one's going to be the 0. So f of 0. What's that? Anybody? What's the sign of 0? Did I hear a 0? Please say yes.
Yes.
All right, good, yes. Sign of 0 is 0, so the first term goes away. How about 2 times 0?
0.
0. And what's cosine of 0?
1.
1. So that's a -1, so this is a -1. Okay, we have a potential minimum or maximum there. Okay, so let's go to the next one. Looks like the next one may be pi halves. So let's do f of pi halves. What's the sign of pi halves?
Sine of pi half.
Yes. Or for those of you who like degrees better, it's 90 degrees, okay? What's that? 1. 2 times 1 is? Did I hear a 2?
2 times 1.
2 times 1, yes. Hard math. What?
Oh, wait, my bad.
All right, get him out of here. No, okay. All right, that's going to be a 2 minus, now what's the 2 times pi halves? I'm doing this part now. Say again? Pi, okay. And what's cosine of pi? Okay, let's write it out. Okay. This is 2 times the sine of pi halves minus cosine of 2 times pi halves. Okay. This is equal to 2 times 1 minus the cosine of pi, and this will be 2 minus, and what's cosine of pi?
-1.
-1, and that would be 3. Okay, we have a potential maximum, don't you think? Still, -1 could be a potential minimum. Okay? So let's go to the next one. I believe the next one is 7/6 pi. So f of 7 pi over 6 is equal to 2 times the sine of 7 pi over 6 minus the cosine of 2 times 7 pi over 6. Okay. Can anyone remember what the sine of 7/6 pi is? Now I'm regretting erasing some stuff. Why?
Is it -1/2?
That was a -1/2. Perfect. Okay. Minus the cosine of, and what's 2 times 7/6 pi? Help me.
14 pi over 6. 7 pi over 3.
7 pi over 3. Excellent. Okay. Now, what's 2 times -1/2? -1. Minus, cosine of 7 thirds pi. You know what I'm going to do? I'm going to go back to my unit circle type thing here. And remember that 1/3 pi is about like that. 2/3 pi is about like that. 3/3 pi, of course, would be there. 4/3 pi would be down here. 5/3 pi would be over here. 6/3, why didn't I start there? 6/3 pi would be right back here. 7/3 pi would be right up here. What is the cosine of 7/3 pi? By the way, that's the adjacent over 1. Anyone want to make a guess? Is my drawing that bad? Yes, don't answer that question. Okay. Somebody? Cosine of 7/3 pi. I would have thought by now you could have done it on your calculator. Anybody?
Is it 1/2?
1/2, you got it. Okay. And what's -1 minus 1/2? Say again? -1 minus 1/2. This is 2 halves, so -2 halves minus 1/2 is -3 halves, isn't it? All right, what do we have? I think we have a new candidate for minimum, don't we? This still looks like a possible maximum, but now this wiped out your 0 as a possible minimum, because -3 halves is less than -1. Right? Please say yes. All right. Now, let's move to the next one. We got this one done. Finally, let's do f of 3 halves pi. That would be 2 times the sine of 3 halves pi minus the cosine of 2 times 3 halves pi. Okay? I'm running out of room, but let's see if we can do it. Yeah. This is 2 times, what's the sine of 3 halves pi?
-1.
-1. Okay? Minus the cosine of what's 2 times 3 pi? 3 halves pi.
-1.
Well, okay, wait. Yeah, okay. I was asking 2 times 3 halves pi is 3 pi. Now I'll ask what's the cosine of 3 pi?
-1.
Okay, yeah, I think you're right, because here would be 1 would be here, -1 here, 1 here, -1 there. You're absolutely right. So this would be, I don't have room to write, -2 minus a -1, which would be, did I hear a -1? Yeah, I thought so. Okay. -1. Okay. If the other -1 didn't work, this one won't either. Okay, so that's out. We have one more. No, we have 2 more. We have 11/6 pi, and then we have 2 pi. I don't know where I'm going to write these. Since we've already eliminated this one, let me write it here. Is that okay? We've already thrown that one out. So let's write it here. F of 11. I can't write. Let me try that again. It's not erasing. Okay. F of 11 pi 6. That's it. That's equal to 2 times the sine of 11 pi 6 minus cosine of 2 times 11 pi 6. Okay. I'm going to need more room than this, am I not? Okay. Anyone know what, I hope with long memories, remember what sine of 11/6 pi is?
Negative 1/2.
Negative 1/2. So we have a 2 times a negative 1/2, okay, minus the cosine of, and what's 2 times 11 pi 6?
11 pi over 3.
11 pi over 3. Okay. Now, the first part I think I can even do. 2 times negative 1/2 is what?
Negative 1.
Negative 1. I got that one. Now, the cosine of 11/3 pi. Okay. Let's do it the easier way this time. 3 will go into 11 how many times? 3 times with 2 left over. Okay. So that's 3 pi plus 2/3 of a pi. Okay. Well, 3 pi would be 1 pi, 2 pi, 3 pi, plus 1/3 of a pi would be this one right back down here. Okay. Now, what's the cosine of that angle? First, give me the sine as in SIGN sine of it. What's the cosine in the third quadrant? Anyone remember? Cosine down here. Cosine in the third quadrant.
Positive.
Okay. All students take calculus. All the trig functions are positive in the first quadrant. Sine and cosecant here. Tangent and cotangent here. Over here it's cosine and secant. So cosine is negative in the third quadrant. So that'll be a minus. And then what's the cosine of, let's do the reference angle. What is that adjacent side of that? Same type deal we had up here. Help me, somebody. It's the cosine of this angle right here. See, don't you miss my arm waving now? Because I can't point out to you where I'm talking about, so I'm trying to do it with the cursor here. What's the cosine of that angle over there in the third quadrant? We know the sine is negative. What's the value of it? Adjacent over hypotenuse. Let me go to a different color, that might help. Carolina blue. The adjacent side over the hypotenuse. Even in my ugly drawing, it sort of looks like it's what? Same thing we had here. What was that one?
1/2.
1/2. Okay, let me go back to black or dark here anyway. Okay. All right. That was like pulling teeth. I feel like a dentist. Okay, so this is -1 minus a minus is plus 1/2. What's that value? I heard something.
Negative 1/2.
-1/2. Okay, that's out of the picture, isn't it? It's the relative max still looks like a 3, and relative minimum is now looks like a -3/2. So I think this one's out of the picture. So let me do some more erasing here. I'll erase this one because that came out -1/2. We're going, well, look at the book and see a picture of all this later. And I think I beat this drawing to death, so I'll get rid of it too. Okay. And I think I can get rid of this one. That can win me a lot of room here, but I'll get rid of it. We want to hang on to that one. I think we can get rid of this one too. That was a -1, I think. I'm getting lost in my sauce here because I don't have enough room to write. So I think those are our two winners so far. So let's try that last value, 2 pi. This shouldn't be too bad. Okay. F of 2 pi is equal to 2 times the sine of 2 pi minus cosine of 2 times 2 pi. Anyone tell me what? Okay, this will be 2. What's the sine of 2 pi? Sine of 2 pi? 0. All right. Minus, what's cosine of 4 pi? 1. So they're back to another -1. So I think we have our relative min, or our absolute minimum. This is our minimum value here, and this is our maximum value there. Okay. Let's look in the book and see what they got. They got 0, -1, and if you remember that, that's what the first one we had. They had pi halves 3, that was our maximum. Then we went down to 7/6 pi, 7/6 pi -3 halves, that was our minimum. Whoops, I missed one. I think I blew one, because 11/6 pi also turned out being a minimum. And I messed it up. I think I've erased it now, so I can't see it anymore. That was also supposed to be a -3 halves pi, -3 halves. I said it was -1/2, I think, or something. That was a -3 halves also. So you have 2 absolute minima, which doesn't sound like it makes sense. This one and that one wound up being -3 halves. I think I messed up a sign. I believe it turned out being -1, -1/2 again, and I blew it, but I've already erased it, so I can't. You can't prove it now. Okay, never mind. So anyway, I messed that one up. And then the last, -3 halves was -1, and 2 pi was -1. Those are nothings, okay? They're not maximum or minimum. Well, actually, the 3 halves -1 is a relative maximum, but it's not an absolute maximum. Your maximum is the pi halves 3, which is also a relative maximum. And your 7/6 pi -3 halves and 11/6 pi -3 halves are both minima, but they're also relative minima as well. All right. Whew. That one was not trivial. It wasn't that bad except the trig part of it. I mean, the calculus part was easy. Now that does finish 4.1. There's a concept check that's always a good idea to go back and review that on your own. But the homework exercises here would be any of the odds 5 through 9. They're all at Calc Chat. 5's at Calc View. 11 and 13, both at Calc Chat. 15 to 23, all at Calc Chat. 15's at Calc View. Any of the odds 25 through 45 on the next page. They're all at Calc Chat. 27's at Calc View. 47 or 49, they're both at Calc Chat. 47's at Calc View. 51 or 53, both at Calc Chat. 55 or 57, both at Calc Chat. 59 or 61, both at Calc Chat. and 63s should be at Calc Chat. You can think about doing 65 if you want to. It should be at Calc Chat. You can explore doing either 67, well, 67 perhaps, that just got a drawing there, and or 69. Okay? Then some applied problems. 71, it should be at Calc Chat. I'd say 71 and or 73. They should both be at Calc Chat. Then you have 2 true false, 75 and 77. They should both be at Calc Chat. And 79 should be at Calc Chat. Any questions? 4.1. Okay. Well, we got about 9 minutes left. I thought I'd wake somebody up with that, but I guess not. Oh, yeah. Jermanuel said, yes, I'll answer to that one. Okay. All right. Let's move on to 4.2. Okay, so what I'm going to do is get out of this one.
Somebody said repeat the last one.
Repeat what?
Chat, you see that?
The homework problems? Is that what you mean? I'm sorry.
He used to put it through. I don't know what he's referring to.
Okay, I couldn't understand what the question was.
In the chat, you should say repeat the last one, please.
Repeat the last.
What the example
All of those numbers are just the last one I said.
No, he just said the example problems. So I guess he's referring to example 4.
Okay. Okay. Oh, wait. You mean example 4, the one that's on the board now? You want to leave that up there for a moment? Is that what I'm hearing? Or you have a question about it?
We're trying to interpret his chat here.
Okay, everything I do to it is making it worse. Let me see if I can just do this.
The count chat problems.
Okay, say that one more time.
You said the count chat problems.
Oh, the Calc Chat. Okay. You want to hear those, all of them again, or just the... I'll do them all if you want me to. Huh?
He just says the last one.
The last one. Very last one. 79. Okay. Any before that? Okay. Y'all are having way too much fun. Okay. So I guess we're through with 4.1? Yay?
Yes, sir.
Okay. So I'll discard. All right. There it went away. So let's end this. We're not ending everything. Whoa! Screen sharing has stopped. No. I didn't mean that. Did I lose anybody? Of course, I won't know because my PowerPoint disappeared. I must have hit the wrong thing. So let me minimize this for a moment here. And minimize this. I need to get my PowerPoint back. So that's here, and here, and here, and here, and 4.2. That's taking most of my time, isn't it? 6 minutes left. Sorry. Okay, are we still? Okay. All right, I think I'm back. Are y'all back? Return to meeting. Here we go. Share screen. Go back to here. 4.2. Oh, wait, I already did that. Here we go. Slideshow. Current slide. I have no idea what. Remove. Please move whatever that says. All right. Chapter 4. Application of differentiation. 4.2. Rolle's theorem and the mean value theorem. Okay. It says my screen sharing is paused. I don't know why. Resume share. Okay, have I got everybody back now? Anybody back? Okay. I thought I had this back up. That one. I thought already from current slide. Okay. My screen sharing is paused again. Resume share. I don't know why it's going around in circles here. Every time I do that, it pauses it. And I don't know how to keep it from doing that. I guess what... Okay. I'm caught in an endless loop here, it seems. Every time I go to open the PowerPoint, it stops the sharing process. And I do not know why. My taskbar down here is not working well. My computer does that sometime. I don't know why. So I can't go to it directly here. So I go to it up here. As soon as I do that, it stops the or it pauses the sharing. Watch me do it. Okay, I get to that, and then I go from current slide right there, and then screen sharing is paused, and I don't know why that happens. Can you hear me? Okay, can you still see the screen?
Yes, sir.
Oh, you can. Okay, I guess.
It's just like a gray block.
What's that?
It's just a gray blob, like JJ said.
I can't hear. What'd you say?
It's just a gray blob, like JJ said.
Oh, that's what the screen shows?
Yeah.
Okay, you don't see 4.2, Rolle's theorem, and the mean value theorem? Okay. And when I do resume share, you see this thing that says Larson, Calculus, ET, F.
4.1 all the way to 4.
Yeah, exactly. Okay. And as soon as I click on 4.2, which is what I want to open, now I want to open it down here because I already, oh, that time it came. No, it didn't. It flashes, but then doesn't let me see if I can make it happen. As soon as I go to click on it again, it goes off. So I do it this way. All right, now time it's better. But now when I go to from current slide, then the screen sharing paused. And I see it, but y'all don't. But the problem is, I think we've just run out of time, haven't we? We're 1 minute off. So since we can't get it, so anyway, I'll just tell you, Rolle's theorem and the mean value theorem. And by the way, who in the world is Rolle's? Okay, that might be a paper topic. Or how did he develop this theorem? That might be a paper topic. Or why did he develop the theorem? Or who uses the theorem? You know, anything such as that could be a paper topic. By the way, he was a French mathematician, Michel Rolle. He first published his theorem. Before that, he was one of the most vocal critics of calculus, stating it gave erroneous results, was based on unsound reasoning, so he wasn't very popular around Isaac Newton or Leibniz, either one. But anyway, we'll begin that next time because I'm pretty sure, out of town. Well, now we are. Sorry that it messed up at the end, but I hope you got most of it, and we'll go from there. Any questions before we leave? All right. Well, thanks for showing up, and we'll do this every Monday and Wednesday morning at 10 o'clock, just like it was class. Even you, Jonah, okay? But we will be here just like regular class and starting in just like regular class. Hopefully the screen sharing will do better than it did today. But take care. We'll see you. Have a good spring break. We'll see you Monday the 30th. Okay?
All right.
Same time.
All right.
All right. Bye-bye. Okay, Houston, still see you, but guess we're ending the meeting. Take care.